All right, take a look at this. I mean, really look at it. It might just seem like a mess of lines and symbols, but this is the kind of puzzle that engineers have to solve every single day. You've got a voltage source here, a current source over there, and resistors sprinkled all over the place. The question is pretty simple though. How do you even begin to solve this?
Now, seriously, where would you even begin? If your first thought is, wow, that looks complicated, you are 100% right. But, complex doesn't mean it's impossible. It just means you need the right set of keys to unlock it.
And that's exactly what we're going to do right now. We are going to unlock these complex circuits by getting the hang of two incredibly powerful techniques, nodal and mesh analysis.
Okay, so here's our game plan. We'll start with that circuit challenge we just saw. First, we'll tackle it with our voltage first tool, which is nodal analysis. Then, we're going to switch gears and use our current first tool, mesh analysis. And by the end, we'll pack it all up into your brand new Analyst Toolkit. Ready? Let's dive in.
First up to bat, nodal analysis. The best way to think about this is as our voltage-first approach. The whole strategy is to find the voltage at just a few key spots in the circuit. And why do we do that? Well, because once you know those key voltages, figuring out everything else becomes, well, surprisingly simple.
And the heart of this method is, you probably guessed it, the node. So what is a node? It's really just a junction point where different parts of the circuit connect. Think of it like a major intersection on a city map. It's the anchor point for our entire analysis.
And the process itself is really clean and systematic. It's like a simple three-step dance. First, find your nodes and pick one to be your 0-volt reference, or what we call ground. Second, we apply a fundamental rule called Kirchhoff's current law, or KCL. All that really says is that a node can't just create or destroy electricity. Whatever current flows in has to flow back out. It's like a traffic intersection. Cars can't just vanish. And third, we solve the equations that this rule helps us build. Let's see it in action.
So, going back to our original puzzle, the very first thing we do is label what matters. In this circuit, we've got two main unknown junctions. Let's just call them V1 and V2. And to make our lives a whole lot easier, we'll say that entire bottom wire is our ground, which means its voltage is 0. Simple enough. All right, on to step 2. At our first node, V1, we use that KCL rule we just talked about. We're going to write an equation assuming all the currents are flowing out of V1. And because current can't just disappear, the total of all those currents has to equal 0. This one simple idea gives us our first big equation, which connects V1 and V2 together.
Now let's just hop over to node 2 and do the exact same thing. We write out another equation for all the currents leaving node 2. You'll notice that 4 amp source is flowing in, so we just treat it as a negative outgoing current. And just like that, we have our second equation. So what do we have now? 2 equations and 2 unknowns, V1 and V2. This is totally solvable.
And here comes the really satisfying part, the algebra. From our first equation, we have a neat little expression for V2, and we can just plug that right into our second equation. What's so cool is you can watch the puzzle start to simplify right in front of you. Once we substitute, one of our unknowns just disappears, and it becomes a straight shot to solving for V1.
And there we have it. After a little bit of rearranging, we find out that the voltage at our first node, V1, is exactly 20 volts. The first lock has just clicked open.
Now that we know V1, the rest is a piece of cake. We just plug that 20 volts back into our earlier expression for V2 and boom, we get our second answer. V2 is 40 volts. We now know the voltage at every single key point in this circuit.
So you might be asking, why does this all matter? Well, because now we can find literally anything. You want to know the current flowing through that 20 ohm resistor? That's just simple Ohm's law, voltage divided by resistance. So 40 volts divided by 20 ohms gives us 2 amps. Just like that, the entire circuit is decoded. That right there is the power of nodal analysis.
But hang on, what if we wanted to come at the problem from a totally different angle? Let's pick up our second tool, mesh analysis. This one is our current first approach. Instead of finding voltages at specific points, we're going to find currents that are flowing in loops.
So the fundamental unit here is the mesh. A great way to think of a mesh is like one of the window panes in a circuit diagram. It's a simple, closed loop that doesn't have any other loops hiding inside of it. Our whole goal here is to figure out the current that's circulating around in each of these little panes.
Let's try this out on a new circuit. The very first step is to spot those window panes or meshes. We've got 2 pretty obvious loops here. We're going to imagine a current circulating clockwise in that first loop. We'll call it I1, and another one doing the same thing in the second loop, called I2.
Our mission, should we choose to accept it, is to find the exact values of these two currents.
Now, instead of the current law, we're going to use its sibling, Kirchhoff's voltage law, or KVL. And this law is also really intuitive. It just says that if you take a walk around any closed loop in a circuit, by the time you get back to where you started, all the voltage gains and drops have to cancel each other out and sum to zero. It's kind of like walking up and down hills on a circular path. You always end up back at the same elevation. Applying this idea to each of our loops gives us the two essential equations we need.
And look at that. We're back to the algebra again. It's the same exact pattern as before. Two equations, two unknowns. Only this time, they're I1 and I2. So we can rearrange and substitute just like we did before to pin down each variable and solve for its exact value.
And after we crunch the numbers, we have our answers. The current swirling around that first loop, I1, is 16/5, or 3.2 amps, and the current in the second loop, I2, is 14/5, or 2.8 amps. We now know the fundamental currents that are driving this entire circuit.
And this is the payoff. Now that we know those mesh currents, we can find any voltage we want. For instance, the voltage across that 30-ohm resistor, it's simply its resistance times the current flowing through it, which is our mesh current I2. And that comes out to a clean 84 volts. Another puzzle solved.
So let's just take a step back and look at what we've really done here. We didn't just solve two random circuits. We've added two master keys to your analyst toolkit. Now you have two distinct, powerful ways to approach any circuit you might come across.
Let's put them right next to each other. Nodal analysis, on one hand, focuses on finding voltage. Its guiding principle is Kirchhoff's current law, and its basic building block is the node. Mesh analysis, on the other hand, focuses on finding current. It uses Kirchhoff's voltage law, and its basic unit is the loop. You see? Two different philosophies, but both lead you to a complete solution.
The best way to think about this is that you are now a master locksmith with two different keys on your keyring. You don't just have the answers to a couple of specific problems anymore. You have a versatile problem-solving toolkit that lets you choose the best way to tackle any challenge.
And that's really why all this matters. These are not just some exercises in a textbook. The phone in your hand, the laptop on your desk, maybe even the car you drive. Every single one of those was designed by engineers using these exact tools. So the real question is, now that you have the keys, what will you analyze next?